Yo, what's up everyone? Today we're going to be doing the stoichiometry slash solutions section of the 2022 USNCO local exam. So this is from questions 1 through 6. Alright, let's get started with question 1. What potassium salt is 28.9 chlorine by mass? So we have potassium chloride, potassium hypochlorite, we have potassium chlorite, and then we have potassium chlorate. We're going to need to calculate the mass percent of chlorine for all of these. So let's get started with potassium chloride. In order to find mass percent, you need to take the mass of the chlorine over the mass of the entire compound. So chlorine has a molar mass of 35.45 grams, and the molar mass is just going to be potassium, which is 39.1 grams, plus the chlorine, which is 35.45 grams. And this comes out to 0.476. So this means that you are 47.6% chlorine by mass in potassium chloride. All right, let's look at potassium hypochlorite. So that's going to be 35.45 grams over 39.1 grams plus 35.45 grams, and then the 16 grams from the oxygen. That comes out to about 0.391, so 39.1% chlorine. Next, potassium chlorite, so KClO2. It's 35.45. It's really a lot of repetition over the molar mass of the compound, and you know the rest. That comes out to 0.333, so 33.3% chlorine by mass. And then the last one, KClO3, it's the same calculation, and that comes out to 0.289, so 28.9% chlorine by mass. And that's what our question asks us for. So the answer for question 1 is going to be answer choice D, which is potassium chlorate. Let's go to question 2. How many sulfur atoms are in 3 grams of iron pyrite? And we're told we have the molar mass here. If we know how many atoms of iron pyrite we have, then we can immediately find out how many sulfur atoms we have. That's because sulfur and iron pyrite are in a 2-to-1 ratio. So if we find how many atoms of iron pyrite we have, we can find out the sulfur atoms. So we have 3 grams of iron pyrite. If we divide that by the molar mass, that gets you how many moles of iron pyrite that we have. And that comes out to 0.025 moles of iron pyrite. This is helpful because we can turn moles into the number of particles using Avogadro's constant. So Avogadro's constant tells us that in 1 mole you have 6.02 times 10 to the 23rd atoms, or molecules, whatever. So if we multiply this number by 6.02 times 10 to the 23rd, we're going to get the number of atoms or the number of molecules of iron pyrite. And that comes out to 1.51 times 10 to the 22nd atoms, or molecules. But that's iron pyrite. In order to find sulfur, we need to multiply this value by 2 because sulfur and iron pyrite are in a 2-to-1 ratio. So this times 2 is just going to be 3.01 times 10 to the 22nd atoms. And that is answer choice C. Alright, so the answer for question 2 is C. Let's go to question 3. A gas mixture contains 50 mole percent hydrogen and 50 mole percent helium. 1 liter samples of this gas mixture are mixed with variable volumes of oxygen. A spark is induced to allow the mixture to undergo complete combustion. The final volume is measured at 0 degrees Celsius and 1 atmosphere. Which graph best depicts the final volumes as a function of the volume of added O2? So for this one, you need to understand what's happening with the hydrogen and what's happening with the oxygen. So let's look at the hydrogen. The hydrogen is going to react with the oxygen to form H2O. And this H2O that you form is actually a gas. So all of these are gases, so it makes sense for the thing that you form to be a gas. And to balance out this stoichiometry, you need to have 2's here. The thing about this is that you're going from gas to a gas. So technically, this shouldn't have a change in volume. You should technically just be increasing volume as you add your oxygen gas. But that doesn't happen. And the reason that doesn't happen is because you're measuring at 0 degrees Celsius. So 0 degrees Celsius is your freezing point of water. What this means is that the gas, the water that's the gas, is going to immediately condense. That means that you're no longer going to have that gas. And so how many moles of oxygen is going to be required to combust the entire hydrogen that we have? It's going to be half the amount of hydrogen that you have. That's because hydrogen and oxygen are in a 2-to-1 ratio in the stoichiometry here. So if you want to combust 0.50 liters of hydrogen, you need 0.25 liters of oxygen. Okay, let's look at what happens with the helium. Now the helium is a little different. So you have helium and you're trying to react it with oxygen. The problem with that is that helium is a noble gas. Helium doesn't react. So what this means is that helium stays there all the time. Therefore, your graph can't ever dip below 0.5 liters. And so that gets rid of B. The helium never reacts, so it's always there. You're just adding oxygen on top of that. So the only time that the volume of the entire container goes down is when you're doing this reaction here. And this reaction only happens with your first 0.25 liters of oxygen. So the answer choice that best shows that is going to be answer choice D. The volume goes down as the first reaction is happening, but after that there's no reaction that's happening. So the oxygen gas just gets piled on in the container, so the volume of the container, the final volume, just keeps going up. So the answer for question 3 is D. Let's go to question 4. What is the concentration of nitrate ions in 40 mils of a 0.25 solution of copper nitrate? Copper nitrate is CuNO3 2. And if you know that copper nitrate has a concentration of 0.25 molar, if you're trying to find the concentration of the nitrate ions, it's just going to be double that. Because for every 1 molecule of copper nitrate, you have 2 molecules of for every 1 molecule of copper nitrate, you have 2 molecules of nitrate ions. So this copper nitrate is going to get broken up into copper 2 plus, NO3 minus, and another NO3 minus. So the concentration of the nitrate is just going to be 0.50 molar, which is answer choice D. All right, let's go to question 5. 1 gram of a transition metal carbonate, MCO3, is heated to produce metal oxide and 0.383 grams of carbon dioxide. What is the identity of metal M? All right, so you have something, MCO3, and it's getting broken down into the metal oxide and also carbon dioxide. You know that you start out with 1 gram of it, and at the end you have 0.383 grams of carbon dioxide. Since the masses must always be conserved in a chemical reaction, the mass of the MO is just going to be 1 minus 0.383, or 0.617 grams. All right, so how do we use this information? We can find out how many moles of carbon dioxide are being produced. And since the metal oxide and carbon dioxide are in a 1-to-1 ratio, it means that for every 1 mole of carbon dioxide that you form, you're also going to form 1 mole of your metal oxide. So how many moles of carbon dioxide are we forming here? We have 0.383 grams of carbon dioxide, and it has a molar mass of 44 grams. So you have 0.0087 moles of carbon dioxide, which means you have 0.0087 moles of your metal oxide. And from this, we can extract the mass of the M on its own, because we know that if 0.0087 moles of your metal oxide is produced, we know that 0.0087 moles of oxygen are also in this compound. So how many grams are those 0.0087 moles of oxygen going to weigh? We have 0.0087 moles of MO, and if we multiply by the molar mass of oxygen, which is 16 grams, we get that in our metal oxide, the mass of the oxygen is 0.139 grams. All right, now that we found oxygen, we can isolate the M on its own. So we take 0.617 grams. That's the mass of the metal oxide that we found over here. And we subtract the mass of the oxygen, so 0.139, and that gets you 0.478 grams of M. All right, we're finally ready for our last step. In our last step, we take the M, the mass of the M that we found, and we find the molar mass. So we know that 0.478 grams of our M represents 0.0087 moles of M. If we want molar mass, we can just set up a proportion and set the bottom equal to 1 mole and solve for X. And once you do, X comes out to 54.9 grams. And out of our answer choices, the only answer choice that has a molar mass of 54.9 grams is going to be manganese. Okay, so the answer for question 5 is A, manganese. Let's go to our last question, question 6. 14 mils of 0.53 barium nitrate solution and 16 mils of 0.44 molar sodium sulfate solution are mixed. Which ions are least abundant in solution? Okay, so we have barium nitrate. Barium nitrate is BaNO3 2. So once that dissociates, you're going to have 1 barium ion and 2 of our nitrate ions. What this means is that nitrate obviously can't be the least abundant, because if nitrate were the least abundant, then barium has to be less than it. So that doesn't make sense. And the sodium sulfate, that's Na2SO4, that's getting split up into 2 sodium ions and 1 sulfate ion. So it obviously can't be the sodium. It's just between our barium and our sulfate. So it can't be B or C. Let's calculate how many moles of barium that we have and how many moles of sulfate that we have. So we have 14 mils of 0.53 molar. In order to find the moles from your molarity and your liters, you just multiply them together. So 0.53 times 0.014 liters, that tells you that you have 0.00742 moles of barium. And let's do the same for our sulfate. So we have 16 mils of 0.44 molar of sodium sulfate solution. So let's do the same thing, 0.44 molar times 0.016 liters. And that comes out to 0.00704 moles of your sulfate. And clearly that is a lower number than the barium, so sulfate has to be the least abundant. Therefore, your answer is D. And that was question 6. So the answer for question 6 is D. And that's all I have. I hope this was helpful. I hope you were able to learn something, and I hope to see you later. Thank you.